Assuming that specific heat capacity of water is constant and equal to 4200, a shell tube heat exchanger, 2 shells and 4 tubes, heats 4,000 kilograms per hour of pressurized water from 35 to 120 Celsius, with 5,000 kilograms per hour water entering at 300 Celsius. So we're using hot water to increase the temperature of pressurized water. That's pretty much it. The overall heat transfer coefficient is U equals 1500. So it gave you U, but you didn't need that U, right? You could go with the name of the coefficient. And the correlation between the effectiveness and the NTU is shown in figure 3. Determine the area required for the heat transfer to occur. So we need area AS. We know, we can look at this guy here at the bottom. We can find area as a function of the NTU because we can multiply the number of transfer units by the C minimum and divide the C minimum by the overall heat transfer coefficient. Now, this fella has been given, so that's good, which means we just need to find these two fellas here to be able to solve this question. So let's start by drawing our little drawing. Again, really insist on this method. I've seen with my own eyes so many students that do this, and it's just trivial. And the ones that don't do this, because it's so easy for them, they get something wrong just because they didn't do this. So trust me, it's a good thing to do it. We have water in both instances, so I'm just going to do cold and hot. According to the drawing, they are in counterflow, but it's NTU method, so it doesn't really matter that much. Cold is entering at 35 and being heated to 120, and hot is entering at 300. The mass flow rate for this guy here is 10 to the 4 kilograms per hour, and the mass flow rate for this fella here is 5 times 10 to the 3rd kilograms per hour. And the CPs on both is the same, and that is C sub P is the same for both because they're both water. So joules per kilograms Kelvin, joules per kilograms Kelvin. Okay, so first thing I'm going to do is I'm going to multiply these two fellas here, mass flow rate and C sub P, because I want to get the big C's, right? So big C's for hot and cold. I am going to maintain the hour unit. If you want to, you can convert. You know we're going to have to convert it eventually, but you'll see why I will maintain it for the sake of this guy here. And this is going to be 4.2. Again, no need for calculators, right? Just looking at things we have. 4.2 times 10 to the 7 joules per Kelvin hour. And on the hot side, we're going to have half of that, so that's going to be 2.1 times 10 to the 7 joules per hour times Kelvin. Okay, so now that we have the values, we can see which one is greater than the other, and that means that this one is our C min, while this one is our C max, just by comparing the values. Okay, nothing extraordinary here. Once we have those values, now check out what we can do. Let's go back to the graph just to see what we're looking for again. We're looking for C min and C max. So, sorry, C min and NTU. C min we already have. So let's actually do it differently. Let me highlight the ones that we're looking for. So we have those two guys already. We're just missing NTU. Okay, so check out. If we already have this ratio here between C min and C max. If we can get our hands on the effectiveness, then we can find the NTU. With the NTU, we can plug it in here and then find the surface area. So all we need to find is the effectiveness, and we should be good to go. What we can do if we want to is we can find the ratio just now because it's just dead in front of us. C min divided by C max is just 0.5, right? So we can just leave this because we're going to eventually need it. But what we don't have at this point in time is the effectiveness, and we need that to be able to solve this question. And we know the effectiveness is the actual Q divided by the maximum possible Q. But note that we have everything we need to find it, because the actual Q, we can use a Q of cold or the Q of hot. And obviously, I'm going to choose to use the one of cold because I have all the data for that. I could do the one of hot if I wanted to. Yes, I could. I could solve this for the one of hot, but then I'll have to find first what is the output of the hot and then plug it in to find what's the Q. Since I don't want to do that because I'm lazy, I'm going to do mass flow rate of cold times Cp of cold, delta T of cold, divided by C min, delta T max. Right? Note that this guy here, this multiplication here, right? Mass flow rate of cold times Cp of cold is our C max, right? 4.2. Right? It's the same thing as C max. We already did this multiplication, in other words. So we could write this as C max times delta T cold divided by C min times delta T max. Okay, let's zoom in into this bit here. This is, what was it, 4.2 times 10 to the 7. And then delta T for cold is 120 minus 35. And then for hot, it was the mean, not for hot, sorry, for the maximum, that was the min, which was 2.1 times 10 to the 7. And the maximum possible delta T I can have is the input of the cold and the input of, input of the hot and the input of the cold, right? So 300 minus 35. Note how convenient this is, because these guys go away. This is just going to be 2, right? 4.2 divided by 2.1, that's just 2. This turns out to be 64.2% or 64%. 64.2%, but like we won't be able to get a 0.2% on the graph, so 64 is just as good. Okay, so we're going to combine the two information that we gathered, which is this guy here. So we're going to combine this and this, and we're going to go to our graph, and with the combination of these two guys, we should get our NTU, right? Let's do it. Again, disclaimer, I'm using a ruler on a tablet. This is not the best idea. Right here in the middle, 70%. So between the two, that will be 65%. If I do one tick closer, it should be the 64%. Oh, come on, stay still. You can see that definitely not straight, but not much I can do here. And the other thing is we are following this 0.5 line here, so it's wherever the two meet. So this would be right here. So we can go down on this line and then see what we come up with. Oh, going down this line might be easier if I do it on the computer. Yeah, there you go. Okay, so we have the line going down. If you look at this value just here, that will be 1.5. So right in the middle there, that will be 1.25. So this guy is anywhere from 1.3 to 1.4, I'd say. Yeah, so it's anywhere from 1.3 to 1.4. I will go ahead and do 1.35. That's the one that I've used before, so I know the mass for it. So I'll say, where is it? The NTU from the graph is 1.35. If you guys got anywhere on that range, that should be 100% okay. No problems at all. Okay, so we can finish off now, right? Because we're looking for the area. That's what we wanted from the start. We wanted the area, and the area was the NTU, which is, there's no dimensions to it, time the C minimum, and we have the C minimum as 2.1 times 10 to the 7, divided by U, which we had but we never used. It's 1500. Okay, one small problem here. You guys identify it before I tell you?
Hours?
Hours.
That's the one. That's the one. The hours, right? So check it out. Let's do the units here. That's why I always do the units, right? See you guys. 1.35, there's no units there. It's just dimensionless. The one on the bottom there, that's watts per meter squared and Kelvin. And then our C minimum at the moment is joules per hours per Kelvin. So if we were to eliminate the things we want to eliminate, we can only eliminate the kelvins because we have joules and watts, joules per hours and watts. So I'm going to push this guy to the side, and I'll multiply what we have by 1 hour on top to eliminate the hour on the bottom, and we know that 1 hour is the same thing as 3,600 seconds. With that, hours eliminates hours, and then joules per second eliminates the watts. And we're left with meters squared, which is a unit for area. So this turns out to be 5.25 meters squared, which is our answer for this one. Okay. Guys and girls, any questions?